All right, so Pythagorean theorem. This is one of those lessons I call it a landmark lesson. All right, this is one of those things that you're going to be using in your math career anyway, year after year after year. Okay, so Pythagorean theorem is super, super important. Why the weird name? Why Pythagorean? Where in the world does that come from?
Oh, from the guy in ancient Greece.
Yeah.
Pythagorean.
Close. You got it. It's a guy, ancient Greece. You got all that part. You got the pith right. Pythagoras. That's the dude's name. That's back when it seemed like everybody just had a first name, okay? Right? Aristotle, Socrates. You ever hear people like that? Okay, Jesus. All right. Pythagoras. All right, so Pythagoras, he wasn't just a math guy. He was a philosopher. He knew a lot of science. He knew math, of course, and all that kind of stuff. He was Greek, and he lived, and I got to read this because I don't remember. I do know it's before Christ. So it's 570 to 495. Wait a minute, I'm going the wrong way. I thought it would go up because it's BC. All right, so he lived 500 years before Jesus did. All right, so it was a long time ago. Now, why do you think they call it the Pythagorean theorem? You'd think that would be true, wouldn't you? All right, you'd think it's because he came up with it, but he didn't. From what I read, people knew about the Pythagorean theorem like several thousand years before Pythagoras. Can you imagine that? Okay, so thousands of years we've known about this Pythagorean theorem. It was known in the day. The Pythagorean theorem was known. People used it, and they knew what it was. But why did they give this guy the name? Because a patent, he was able to, from what I understand, I'm not a great scholar on this, okay? I just kind of quickly searched. But from what I understand, he was the first one to have proven this theorem, okay? And what is the theorem? We should know it, right? A squared plus b squared equals c squared. Now, I could just say, here it is, this is how you use it, do the homework, right? But I'm not going to on this one. I wrote out a little proof. Now, there's a lot of proofs. Remember that video I showed you yesterday? I hadn't seen it before, right? We had like less than 10 minutes left in class yesterday, and I just wanted to show you something. So I looked it up real quick. As I was looking up, there's all kinds of proofs of the Pythagorean theorem. There's not just one way to prove it. There's a bunch of different ways to prove it. And I'm not, again, a scholar on proving the Pythagorean theorem. All right, so you can look it up. There's a lot of stuff online. Go on YouTube. In fact, just recently, I don't know what, maybe a few years ago or something like this, these two high school girls, came up. I don't know if they came up with it on their own or not. You can watch the videos. If you just put Pythagorean theorem high school girls, it'll come up, okay? And these two girls came up with a brand new way of proving the Pythagorean theorem that hadn't been done before, all right? Which is kind of cool. Now, how did they do it? I don't know. I didn't watch the video, all right? Again, I'm not a scholar on this. I haven't done a deep dive on it, but that's kind of interesting. So on your own time, you should look at it. I mean, kids your age came up with a brand new way to prove the Pythagorean theorem. All right, we're going to do it. I did it one way. I don't know where I got it. I think the book probably did it like this. But there's a bunch of ways, but this is kind of interesting. So what we're going to do is a little proof of the Pythagorean theorem and show you, and hopefully you'll understand where it comes from. All right, so what I'm going to do is I'm going to put a square inside another square. I'm going to make the second square smaller. So I don't know what color. Let's go red. Is that right? And then we'll make the outline red as well. Okay, so I'm going to make another square. Let's start about right there. Don't draw this just yet. In fact, just sit back and just watch and just enjoy the journey here, okay? I'll tell you when you can start writing stuff. If you want to write this down, that's fine. But what I'm going to do is I'm going to tilt it a little bit, about like that. And then I'm going to try to get this. I might have to rearrange how big this is, but I want to get it to fit inside the white square. Oops. There we go. So I'm just trying to manipulate this just so it fits right on the, so each vertex fits right on there. That's close enough. Maybe not exact, but it's good enough. We good with that? Tell you what, let's do this. Let's make the outside of this red just so it has a little bit of boundary to it, okay? Now, what I'm going to do is, let's just do different colors. I'm going to call, so I've got this square inside the white square, okay? Look inside here, though. What is this thing right here? It's a triangle, and it's a right triangle too, isn't it? Okay, why? Because I started off with a what? With a square, right? So it has to be a right angle. So this is a right triangle. How many right triangles do we have? 1, 2, 3, 4. Now watch this. Let's call the short one A. All right, so this triangle down here, I'll call that A. This short is A, and this one right here is A. Everybody see what I'm doing? All right, so I've got this right triangle right here. I'll call this side A, right? And then it's the same triangle here. They're all congruent triangles, okay? If I was able to, I don't know how to do this on this program, but if I was able to cut them all out, you'd get another square, okay? You follow me on that? So if I took this, put this next to it, put this around it, I would get another square. But I'll call that A, and then I'll call the longer side. So this is my shorter side. This is my longer side right here. And they could be the same lengths, to tell you the truth. It doesn't matter. I'll call that B. I'll call this one B. I'll call this one B. And I'll call this one B. Everybody good? Well, what's the Pythagorean theorem? A squared plus B squared equals what? C squared. What is the C in the Pythagorean theorem? It's the hypotenuse, okay? So this one right here would be the what? That would be the hypotenuse. So guess what I'm going to call that? Call it C. I'll put it inside there. So that's C, this is C, this is C. How do I know all four of those are the same? Because this red thing is a what? It's a square. You with me? Okay. Everybody on board? All right. Don't lose me. We don't do too many proofs in here, but this is a good one to do. All right. So now what I'm going to do, I got to look at my notes a little bit. So I got the big square, the white square. I got the little square, which is the red square. And then I got all these triangles. Okay. How many triangles do I have? How many triangles do I have? I got 4. And they're all the same. They're all congruent to each other. Okay. So they're all the same. What I'm going to do is talk about the area. All right. We're talking about area in this chapter, correct? Yep. So I'm going to talk about the area of these things. So let's talk about the area of I'll tell you what, let's stay color coordinated here. So let's talk about the area of the white one. All right. So I'll do that in white. So what is it? The area of, if it's a square, correct? So what's one of the lengths of the square? The white square. What's one of the sides? What's one of the lengths of the sides of that white square? Svanka, you with me? Come on, snap out of it. Pay attention. Let's play along here. Play the game. So what is it? A plus B. Very good. So this whole side right here is what? It's A plus B. Well, what are all the sides since it's a square? The A plus B. Everybody see that? So if I was going to find the area of that white square, the whole entire white square, everything included inside it, everything, the whole entire white square, what's that going to be? A plus B times what? A plus B, because it's base times height, correct? Length times width. Side times side, or side squared. Agreed? All right. So now what I'm going to do, so I'm going to do a little bit of math. The math that I'm going to do should have been covered in Algebra 1. Sometimes it's not. All right? It might be. You know FOIL method? Did you learn the FOIL method? First, outside, inside, last. Remember that? Okay, that's what we're going to do right now. I don't think we've done that all year, have we, in here? I don't think we have, but we're going to do it now. So if I multiply the first terms together, what do I get? It's this times this. What's that? A squared. Then I do the outside. What's the outside? Plus A times B. So that's plus AB. What about the inside? These two. What's that? You could say BA, but you could switch the order too, couldn't you? We'll just keep it AB since I made that one AB. Everybody okay with that? Plus what? The last, B times B, B squared. We could add those together. They're like terms, correct? That's 1AB plus what? 1AB. So that's A squared plus what? What's 1AB plus 1AB? I can't hear you. You're mumbling.
Oh, B squared.
B squared? 1AB plus 1AB?
Oh, AB squared.
If I got 1AB, and then I got another AB, how many ABs do I have? I got 2 of them. So I got what? 2AB. You with me? So all I did was just add those up. Then what's last? Now you can say it smarter. B squared. Good. So that's the area of the white one. I'll just keep it in the color. I won't even say the white one. I'll just put it 2AB. Actually, I should say it because my triangles are white too, aren't they? So let's name it area of the big square. I'll just put SQ. You with me? Oh, I messed that up. Plus B squared. There we go. So that's the area of the big square. How are we going to use that? Well, we'll see in a minute. Okay? So let's keep that in mind. Let's put it in a box for safekeeping. All right, so now what I'm going to do is I want to find the area of the small square. So area of the small square. And I should make this red, shouldn't I? Since the small square is red. All right, this is a little easier. So how do you find the area of that red square right there, the small one? Is it c squared times c squared? It's just c squared, right, because it's c times what? C, all right, which is c squared. We good? Okay. Let's do, tell you what, we'll do this in blue since I kind of made the sides in blue, even though the triangle's not blue. Everybody okay with that? So let's do the area of the 4 triangles. All right, so what do? Find the area of one of the triangles. And then do what to it? To find all 4. Multiply by 4. Good. Okay? So what's the area of just one of these white triangles? Like this one right here. What would the area of this triangle be? Well, first of all, it's what? 1/2, right? Because the area of a triangle is 1/2. What? Base times height. What's the base and height of this? A and B. That's right. So 1/2 A and B. Agreed? That's one of the triangles. How many do I have altogether? I got 4 of them. So what am I going to do? Multiply by 4. Yes? Equals what? 4 times 1/2, or half of 4 is what? 2AB. All right? I put that in a box. I forgot to put those in boxes. I'll tell you what, I'll just take that box away. All right, I got the white one, the red one, the blue one. Red, white, and blue. I didn't even try that. Yay, America. All right, so watch what I'm going to do. I am going to actually try to solve for c squared. Why do you think I want to solve for c squared? Because my Pythagorean theorem is a squared plus b squared equals what? C squared, correct? So let's see if it really works. So the area, what should we do? You want to do this? Let's do the big one, okay? So watch this. If I took the area, I'm just going to do everything in white now. I'm not going to try to color code it, all right? So the area of the big square equals the area of the what? Small square plus the area of the what? The 4 triangles. That's right. The 4 triangles. Agreed? But again, what do I want to get by itself? I want to get the small square by itself. How do I get the small square by itself? So the area of the small square is equal to what? Area of the big square minus the area of the 4 triangles. Okay, let's watch. So stay awake. Everybody here? Okay. So I'll tell you what. Let me, I don't know, can I fit? Yeah, I can fit it all in there right there. Okay, so let's plug it in. What's the area of the small square? What is the area of the small square? It's c squared. So watch. C squared equals, what's the area of the big square? All that stuff, right? So let's write it down. A squared plus what? 2ab plus b squared. Minus the area of the four squares. What's the area of the four triangles? I'm sorry, not squares. The area of the four triangles. What is that? It's 2ab. So what can we do to make this look a little bit nicer? 2ab, what? Minus, see where I'm pointing? 2ab, what? Minus 2ab, what happens there? Okay, they add up to 0. So what do you got left? C squared must equal what? A squared plus b squared. Check this out. If you just want to rearrange it, what can it be? A squared plus b squared equals c squared. There you go. I'll definitely put that in a box. And that is the what? Pythagorean theorem. Pretty cool, huh? So we just proved it. All right, so somebody stops you, taps you on the shoulder. Please, I'm doing Pythagorean theorem. I need you to prove it for me. Okay, I gotcha. Take this take this square, put this little square inside there, a plus b, c squared. Okay, all right, now you're ready for it, aren't you? All right? Yeah, just let me know if anybody taps you on the shoulder, asks you to prove Pythagorean theorem. I don't know, it might be me. I might ask you. All right, so somebody asked me, remember we talked about a 3, 4, 5 triangle? Who was it? Xavier, you asked me, are there any other ones, right? With 3, 4, 5. So this is called, these things right here are special types of Pythagorean theorem triangles, all right? We call them Pythagorean triples. There's probably a lot more, but 3, 4, 5 is one of them. So that means if I have a right triangle, remember this only works with what kind of triangles? Right triangles. Because when I did this proof, this was a right angle, that's a right angle. These were all right triangles, agreed? So it only works with right triangles. So you can only use this. Write it down. Put it in parentheses or something. You can only use this with right triangles. All right? Pythagorean theorem only works with right triangles. Can't do it with an acute, can't do it with an obtuse. You can only do it with right triangles. We good? So if I had this is 3 and this is 4, let's actually do the Pythagorean theorem to solve for C. So what would that be? That would be 3 squared plus what? 4 squared equals C squared. Agreed? 3 squared is 9. 4 squared is 16 equals C squared. 9 plus 16 is 25 equals C squared. How do we get the squared go away? How do we get just C by itself? No, you don't divide by 2. It's not 2 times C. What's the opposite of squaring something? Taking the square root. Take the square root of both sides. The square root cancels that square. You see it? So what's the square root of 25? That's 5. So C is equal to 5. It's not always going to come out that pretty and nice. Okay? Some of you guys have to snap out of it. Come on. Wake up, wake up, wake up. This is where we're doing the... somebody tap him, please. Somebody... they're not always going to come out nice and pretty like this with all just whole numbers. Okay? But there are some that do come out to nice, pretty whole numbers. And I'm going to give you just a short list of some of them. This is super helpful. You guys heard about people taking the PSAT and the SAT and all that kind of stuff. There's questions, at least a long time ago. I haven't looked at the most recent SAT test, but there's a lot of times you'll see problems where you might have to find one of the other sides, but you could do it very, very quickly and easily without really doing any math. For instance, what if they said that was 3 and that was 5 and they asked you to solve for x? You should be able to do that without doing any math at all. Look at it. It's a right triangle. The hypotenuse is 5. One of the legs is 3. The other leg has to be what? 4. Do you see how we could do that? So it's really nice to know your Pythagorean triples because sometimes they'll give it to you and that'll save a lot of work. Doesn't that save a whole bunch of work? Absolutely. All right. So here's some other ones. 5, 12, 13. These are dashes, by the way. It's not being multiplied, okay? 5, 12, 13. 8, 15, 17 is another common one. And then another one is 7, 24, 25. And if you wanted to, we're running out of time, but if you wanted to, you could do this and see if it really works, okay? I'll do one of them. We'll make that 5, that 12. Remember, the biggest number always has to be the what? The hypotenuse. So let's see if you actually do get a 13 with this. Everybody watching? So let's put it in the Pythagorean theorem. Let's call it C. I'm going to put C to the left. Instead of a squared plus b squared equals c squared, I'm going to go c squared equals a squared plus b squared. Is that all right? Yeah, because we're trying to solve for c. So I'm going to put that first. So equals what? It doesn't matter which one your a or b is, but they're the legs. 5 squared plus what? 12 squared. So c squared equals 5 squared is 25. 12 squared is 144. C squared equals 169. All right, maybe you don't know this, but if you take the square root of both sides, C is equal to 13. All right, so it comes out to a nice whole number. You got it? Or an integer number if you want to, but whole numbers because they'll never be negatives anyway. So whole numbers. So C is 13. I could do that with all these just to check, but trust me, they work, okay? Everybody okay with that? Yeah, so let's do an example. And then I'm going to teach you one more thing. Now this, oh my, they give you I can't believe, I guess I could believe it. They expect you to have had a very rigorous Algebra 1 program, okay? Especially on this example. What are we at, 10 after? I got 12 minutes. Let's skip example 1. I want to get back to it because you are an honors class. You definitely need to see this. This is definitely something that I would not give to my CP class. All right, but I will give it to you, but let's go over it on Monday. All right, example 1. I will go to example 2 though. All right, just because the algebra is just going to take too long to explain. All right, if you guys had a really rigorous Algebra 1 class and you knew about factoring. Did you guys do any factoring in Algebra 1? You did a little bit of factoring? Okay. So on Monday, we'll go over it, okay? I don't want to skip it. I do want to go over it, but we will go over it on Monday. So let's do example, not 1, but 2. It says, find the area of this equilateral triangle. So equilateral means what? All the what? Oh, why did I put ellipse here? Hold on. Polygon, that's what I wanted. Okay, let's go to 3. There we go. So there's an equilateral triangle, and we're going to find the area of it. Make it a little bit bigger. Okay, we're going to find the area of it, and they're going to give you some information. So they give you this, they make this a dotted line, but I can use color, so I'm going to make it a color. All right, so they tell you that. They tell you this is 8. They tell you this little bit right here is 4. Where is that 4? Is it the whole bottom? No, it's just from this red to the end. Okay, so that's 4. And then they ask you to solve for the height. There you go. Can you do that? Well, we're going to use Pythagorean theorem. We'll go back to the a squared plus b squared thing. Okay? What do we put in for here? What do I put in for the a? Yeah, you could put the 4, or you could put in what else? The h. Right, let's do the h. Since that's what we're going to solve for, let's put that first. Is that all right? So either one of the legs you could put in for a and b. Only the hypotenuse is the c. Everybody got that? So only the hypotenuse. Smart. Come on. If you'd be writing this stuff down, it would help you stay awake. Not writing stuff down makes it easier to fall asleep. So let's put an h in for the a plus the b squared. What's the b? Because I got this right triangle. That's what I'm looking at, isn't it? Okay. So what is this? What's the b? It's 4 squared equals c. What's the c? It's 8. They tell you the c, the hypotenuse. Now, what you have to do is just solve for h. It's a little bit of algebra, not that big of a deal. H squared plus what? 16 equals h squared, which is 64. Subtract a 16 from both sides, and that is, what is that, 48? Is that right? Yes, 48. So h squared equals 48. What do we do now? H squared equals this. What do I do to get rid of that square? Square root both sides, okay? So now, here's something I got to teach you. I got a couple minutes here so I can do this. The square root of 48, I guess you could write it down. I guess you could put it into a calculator, but what I'm going to do is I'm going to simplify this. Again, this is something an Algebra 1 class would have taught you, but maybe you did, maybe you didn't. So the square root of 48 equals. So what I'm going to do is I'm going to break this down, hopefully into two numbers, something times something else, and you can take the square root of one of those numbers. What is it? 6 and 8? Can you take the square root of 6 to get a whole number? Can you get, 16 would work, okay? So you could go 16 times what? 2, correct? I'm sorry, 3. 16 times 3. Or you could do what? What else goes into 48 that you can take the square root of? 4. 4 times what? 12. You could do that, but then you would have to take that 12 and take that 12 and break that down further, all right? 16 times 3 is perfect because square root of 48 is the square root of 16 times 3. I think I've talked about this once or twice in this class. Remember in algebra, when you have a square root like this and it's being multiplied, you have a rule that says that you can break them both down into their own square roots. See? Square root of 16, square root of 3. Everybody with me? Now, you know what the square root of 16 is. What is it? It's 4. Can you break down the square root of 3 anymore? No, so you just leave it, the square root of 3. So h is equal to what? 4 square root of 3. This is something that I'm going to want you to do. As an honors class, I want you to be able to simplify these radicals. That's what they call it. That little check mark looking thing, that square root, it's called a radical. And it's something that I'm going to want you to be able to do. I would not force my CP class to do that, but you guys, I want you to be able to do it. All right? Now, what is the question, though? I didn't even write the question down. What's the area of the triangle? Okay? So, how do I find the area of a triangle? It's 1/2 the what? The base times the height. Well, I just found the height. All my work was really finding the height. Finding the area is not that big of a deal. So I found the height. What's the height? 4 square root of 3. So now, how do I find the area? The area is 1/2 times the base. What's the base of this triangle? Is it 4? It's 8. It's this whole thing from here to here. Remember, it's equilateral triangle, so this is 8. So it's 1/2 the base, which is 8, times the height. What's the height? We just found it. We did all that work to find the height. Okay, so really, the bulk of this work was just finding the height of this triangle. Now let's do this. 1/2 of 8 is 4. 4 times 4 is 16. And then square root of 3. So forget that, equals. Area equals 16 times the square root of 3. You got to speak up. That's right, because you can't simplify it. Now, technically, you could put this in a calculator, get a decimal answer, but a lot of times, especially in high school math, we don't put it into a calculator. We just keep it like that, all right? So this is really a good way to write it. Oh, I didn't put the units, but I didn't tell you what the units are. I just wrote it in a second ago. Okay, everything's in centimeters, so area is what? Centimeters squared. And that would be the answer. You could put it into a calculator, but a calculator gives you an approximate answer. That's why the 2 squigglies. Everybody see that? This is exact. This is what? Approximately. I'll just put approx. All right, and you put it into a calculator, you get 27.7, and then it's also in centimeters squared, okay? Either one of those would be okay, but look, you can do this without a calculator and leave your answer like that. This is an exact answer. This is just an approximation. Let me do one more thing, and then we'll be ready to stop. Let's go different color. Use too much red on that one. All right, so this next thing they call the converse of the Pythagorean theorem. So let's do this. If c squared equals a squared plus b squared, what kind of a triangle would it be? If c squared is equal to a squared plus b squared, what kind of a triangle is that? It's a right triangle. Okay? Now, watch this. We only got a couple minutes, but it's not going to take long. If c squared, watch this, was less than a squared plus b squared. So you got to square it, okay? It's not just that it's got to be less than this. If c squared is less than a squared plus b squared, what do you think? If this is a right triangle, then this would be an acute triangle. Because less than, when I think less than, I think what? Less than 90 degrees, right? If it equals 90 degrees, it's a right triangle. So equals is right. Less than is what? Acute. So what do you think the next one is? If c squared is what? Greater than, let's use greater than, a squared plus b squared, then what kind of a triangle do you think that is? This would be obtuse. All right? Everybody see that? So I can tell without even drawing it or anything else, just by putting those numbers in, I can tell if it's what kind of triangle it is. So we got 1 minute. So watch. What if I had 7, 12, and 13? And I wanted to see what type, what do they say? Well, it says, is it right, acute, or obtuse? Okay, I'll just put what type. So what type of triangle is this? Everybody watching? So what do? I take the c squared and I put it first. Which one is the c here? 13, okay? So make sure you do this correctly. Don't pack up, I'm not done. So watch, you take the 13 and you square it. I'm going to put a little question mark right here, okay? Because I don't know right now if it's equal, less, or greater. So let's do the other one. So what do I do now? 7, whoops, what happened there? 7 squared plus what? 12 squared. And let's put those in. 13 squared, we've already done that. That's 169. What's this? 49 plus, what's that? 144. This comes out to 193. This is 169. So what is 169 compared to 193? It's less than. So what kind of a triangle is this? It's an acute triangle. Okay? And that's how we can just look at the numbers, do a little math, and see if it's right, acute, or obtuse. We good? All right. Good timing. We got some problems to do then. Looks like I split this up into 2 sections, so we'll call it section 7.3a. All right, and it's pages 314, 315, and it's numbers 1 to 10. Don't get too excited. And it's 13 to 19. That's not too bad. Everybody good? Is that 16 problems? 17, right. Because look, some people think that's 6 problems. It's not. What? Because you went 19 minus 13, right? But look, if you go 10 minus 1, does that mean that's 9 problems? No. So you got to count the 1, don't you? So how many problems is this? 7. Okay, a lot of people get that confused. All right, so it is 17 problems. Everybody good?